Hi guys, good morning. In this video, we're going to see problem minimum path sum, but before that, sub changasi. I hope so. If not, then you can just let me know and I can probably help you out. But yeah, let's start this problem. A minimum path sum, it says that we are given a m cross n grid, m rows and columns with non-negative numbers. Numbers are positive and can be zero also, but can't be negative. Path is defined from top left corner, which is this corner, to the bottom right corner, which is this corner. So any path you take, which means any cells you take to start from source as top right, top left and destination as bottom right, then any path you take, it's a path. We to choose a path which minimizes the sum of all numbers along its path. So as you can see that, okay, if I have a cell at top left and a cell at bottom right, I have to reach from the cell right here to right there. Then I have to choose a path, and they can be multiple paths, like this, like this, like this, like this, any path. So let's firstly think very brute forcefully. How? Let's just print all the paths. Let's just grab all the paths. Let's just grab the sum of those paths. And probably after that, what we can do is just see what is the minimum sum. Let's see the same thing. Firstly, what we have to do is minimize out of all the paths. So let's grab all the paths itself. If I'm standing at a node, I have two options. Either I can go right or down. If I'm standing at a node right here, I have again two options, right or down. So if I'm standing here, I just land here. Maybe if I choose to go down, if I'm standing here, I just landed maybe here, then again I landed 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 here, then maybe again I landed here. So you can easily see that in worst case, it can just go like this from here to here, then here, then here, then here, then here, then here. So at every time it is just going forward and also down. So I can just say that, okay, at every cell, I have two options. Either it can go down or either it can go right. So I just know, okay, I have for a cell, I have two options. But in worst case, how many cell it can iterate? As I showed you, right down, right down, right down. So here also two cells have been done. Here again two cells are done. Here again two cells are done. Kind of you can see that, okay, every row is being used and every column is being used. So it is that I have n plus m cells roughly, because either last starting cell will not be counted, but roughly n plus m cells I will be there. In worst case, for that I can just choose both the options. Either can go right or down. As I have both the options are 2. So for every cell I just multiply it by 2. So in total, the complexity will be 2 raised to power n plus m. Firstly, my n is less than 200, but still it's exponential. It can't be done. So grabbing all the paths I can get, but grabbing all the paths and finding the minimum won't work. Can we do something else? Let's break this statement. Grabbing all the paths and choosing the minimum path. How about I only choose the minimum path? How about I only choose the minimum path, which means I'll just try something that I am only choosing the minimum path. How? So firstly, let's see what was happening, like why this complexity is so much exponential and how I can reduce it. So okay, I just know one thing. Okay, I can just choose the minimum path, but which algorithm to apply, how to know, Aryan? How I would know? I just know, okay, the statement says that print all the paths, or like, let's say, have all the paths and grab the sum of those paths and choose minimum. You said that, okay, it's not possible, it's exponential, but how you will achieve and what you will do, how you will think. So if you clearly see how the paths will look like, it will look something like this, right? I have one path, let's say here, one path, let's say here, one path, let's say here, and so on. So you can clearly see, and when I say path, I'm just grabbing the sum. Like I grab the sum here, 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 and here. I grab the sum here, 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 and here. Grab some here, 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 and here, and here. So you can easily see the sum right here, it's same as that of sum right here. So if I have this particular sum of this thing, I can just use that sum to actually compute here. So I don't need to recompute it again and again. You saw the words I was using. I don't need to recompute it again and again. Do you remember anything? What algorithm is being used when something occurs again and again, but we just want to store it in memory so that we can use it later? Nothing but your favorite DP. So we for sure know, okay, as we have a sub problem which we can use for later, which is the sum for sure, then I can actually use a DP. Okay, I can use a DP, but how to store the sum? As I said, I just know, okay, I can't print all the paths to get the minimum sum. How about just get the minimum sum itself? So what I will just do is I'll just grab the minimum sum itself, which means I'll just choose greedily. If I am at a cell, right? If my starting is here, if let's say the cell is something like this, I'm standing here right now. I started from here, so I have one option is I can go right and turn down. Another option is I can go down and turn right. So basically, it is both. It is common in both of them. The only difference is the elements right here. So it will only affect what is the best minimum possible path from here up till here. From this S to D, what is the minimum possible path? Just choose the minimum out of these two. And it will, basically I'm just greedily choosing the minimum path so that, okay, I'll ultimately move to only that part because all the elements are positive. Which means no matter what in future, I'll just add something positive in my row. So it is pre-ahead should be pretty sure. I should be pretty sure whatsoever I am grabbing, I should grab as minimum as possible, as minimum as possible, as minimum as possible. That I'm doing here, which means that, okay, firstly, as we already know that, okay, if I am at a cell, then I need to grab the element from the top and from the left. What if I'm grabbing the row at the top itself? It has no top element. Or what if I'm grabbing the first column itself? It has no left element. So firstly, let's make the first row and the first column. Let me show the first column greedily by ourselves. Okay, because see, ultimately if I have a 1 value here, I'm using the same example as right here, 1 3 1 and so on. So if I have 1 right here, what is the next? If I just move on to this path, then what is the next sum? 1 plus the current element, which is 3. So the next sum is 4. Now I just have to grab on and move on in the same path because it's just a straight line. So I'm just at every cell, I'm just storing the minimum possible sum to reach that particular point. So to reach this point, I just grab the value from behind, which is 4, and its value, it was 1. So I get the sum as 5. So you can easily see that, okay, I just got the values as 1, 4 and 5, which is, if I just move on, I just get the minimum sum as 1, minimum sum as 4, minimum sum as 5. And I'm just iterating it so that, because ultimately I just know I just have to not choose up and left. And same I go for the first column, which means its top element is 1, its current element is 1, so the sum is 2, its sum is 2, the current element is 4, so sum is 6. Okay, I got the left sum, I got the top sum. Now let's grab the element right here. If I am standing at this particular box right here, I'll see above, I'll see left. My left is less, so it's always good to come here. So I'll just grab what is the sum. See, this particular 2, it stores the sum from here to here. I'll just add this element, which is this, so as to get the sum from here to here to here. As simple as that. So I just grab this sum, which is, I just grabbed this left sum, which is 2. I just grab the current value, which is 5, so as to get this L-shaped sum, and my sum, what I got is 7. It will indicate me, okay, if I have only the particular matrix right here, then I can just reach from 1 to this particular node, which is last node. Minimum sum is 7. Same I go for this particular cell. I just grab, like, it is top, it is left, my top is less, so I just grab that top, current element is 1, answer I get is 6. Then I just grab it, I just see, okay, 6 and 7, 6 is minimum, current element is 2, I get a 8, 8 and 6, 6 is minimum, current element is 1, I get a 7. And you remember one thing, I ultimately wanted to reach what? The bottom right cell. It is the cell, and it just indicates, okay, what's the sum like to actually reach to this cell, and ultimately I can get a 7, which is the minimum sum, because I greedily choose the minimum sum, and that is the reason I just got the minimum sum possible to reach from top left to bottom right. And that is the whole intuition, whole thing of this problem. Okay, firstly we thought, okay, how to optimize, which algo to use, by just seeing, okay, what was the problem in our existing algo. Then we just reverse the problem a little bit. Okay, rather than grabbing all the paths and grabbing the minimum sum, how about if it is possible to grab only the minimum path sum? And to grab that, I just use the greedy approach. Why greedy? Because all the numbers were positive. So it's always good to me that, okay, I just grab the minimum sum as minimum as possible. Now, okay, to implement this, now you get the answer. I'll recommend to implement this, but to implement this, I have many ways. Firstly, the very, very, very optimal way is, if it is the most optimal way, it is just that, okay, I'll just grab on the complete matrix one by one, and I'll just grab this particular sum. See, I just wanted to, I have this matrix, let's say grid, and I want to have this sum. Let's name this sum. So either I can just use another matrix as sum, or I can just overwrite this particular matrix as grid, because after using this value as, see, after I grab this value as 7, I don't require this value, right? So I can just use the same matrix grid to actually store the sum. I'll just use that. Firstly, I just make the, as I said, first column and first row. I just have them separately, first column operation and first row operation. After that, I just move on to every cell from index 1 up till the last index, and I just grabbed, okay, what is the minimum from top left and the top and left, and also I added the value which is actually the grid value, because I just grabbed the minimum value out of both of this and added the value itself, which was actually present at this particular index. Cool, I just did it. It will just give me the sum, and ultimately I have to return the last index sum, because I just wanted to reach that last index. And it is space is O of 1 because I'm not using extra space, I'm just reusing that grid part, and complexity is O of n into m because I'm iterating on every element of that grid. But what if the interviewer says that, okay, you can't modify this grid, maybe the grid I have to use later, so you can't modify the grid. What's the next approach you have? So the next approach which we can have is very simple. Make another matrix as sum, as we were doing that. Okay, rather than storing in grid itself, let's make another matrix as sum and use that matrix. Space complexity will be O of n into m. Time will remain same because I'm just making another matrix, and it's nothing like the same operation which we were doing in grid itself. I'm doing it in another matrix. Okay. Can we optimize it? Like the space from O of 1, I just directly reach to O of n into m, because I just can't use or can't modify the grid. But still, can I optimize it? Yes, for sure. You remember one thing, what happened? Firstly, it is exactly same code. In this, I just uses this sum, exactly the same thing. I just use this sum, and now every operation of storing the element or storing the sum is in the sum matrix itself. To optimize the space, you remember one thing, what happened? If we are at a cell, I was just looking at the cell from the top and from the left. If I'm the cell right here, from the top and from the left. If I'm the cell right here, from the top and from the left. Which means at any point of time, if I want to compute sum of I and j, I was just looking at sum of I minus 1 comma j and sum of I comma j minus 1. You can easily see that for any point, I'm just looking at sum of I minus 1 comma j and sum of I comma j minus 1. At any point of time, I'm just looking at, okay, what's left and what's top. So if I just want to look at the left and top, I have to store the whole matrix. Why I can't just store one row for top, one whole column for left? I just keep on shifting it to actually grab my value. And this is the whole thing of this problem, that okay, I just grab this one column from the left, I just use one rows, I just can shift the rows, because see, if I want to compute the value at here, I just want the value from here, from the top and from this left thing. So I just grab this value. If now when it is done, I can just assign the same value here. Now my array will come down. Now my new array is this. Now when I want to grab this value, I just want the above value and from the left, above and from the left, and I am good to go. With this, I can just use a top, like a array, which will represent me the top elements, and the array which can represent the left elements, and I'm just good. With this, I just get a complexity of O of n plus O of m, one for the row, one for the column. That looks good, but can we still optimize it? Can we? Yeah, we can. You thought one thing what happened. Let's see. If I was using this prefix sum, let's name it as current array. So what was happening is, to get the value, let's see, to get the value right here, what I will do is, I will use, see, here the value is, if the array name is current, so here the value is current 0, here the value is current 1, here the value is current 2, right? So to grab this value of current 0, I can just grab, okay, what is the value of current 0 here? Because see, I'm just reassigning current 0, but until the current 0 is reassigned, it has a value of current 0 which is here, because current 0 was actually here, plus the grid value, it is actually the new current value. So my current I, the variable remains same, but its value just got shifted to here. Variable I use the same. I just use its last index value, which is this value, grid value, which is actually the value present right here, to actually get the sum up till this particular index. I get a new current value. But Aryan, how will it help me? Let's see. If you have this current of 1, because see, current of 1 was right here, my current of 0 is updated with this. It is no more here. It is no more here. Now, if I want to grab the value right here, I'll just see what is the current of 0, what is the current of 1. I just grab the minimum out of these, and I'm just good to go. Which means that to grab this current of 1, I'll update this current of 1. This current of 1, I'll update it as I updated my current of 0 to here. I'll update this current of 1 to here by using what? By using above current of 0, which is the updated current of 0, and also current of 1, which is this current of 1, and grid of I plus j is always added because it's just the value at that current position. So you saw how are we doing? We are just moving like this, and as soon as I want this particular value, see, we are just moving like this, and then like this, then like this, like this, like this, right? So I'm just moving column wise. So if I am completed with this first column, and I am also completed with this, I landed here. I am completed with, so I have this updated current 0, existing current 1 I have, so I can get a new current 1. Same, it will go again. It will just, again, let's say it just goes again, it starts again. You will see that, okay, I'll just grab a new current 0, then it is the existing current 1. With this I can get a new current 1. It is the whole thing which you have to see in this problem, that firstly I just grab this whole prefix part, as I said, because after that I'll just start from this first column itself. So I start from the first column, I'll just go on. See, I'm just going like this, iterating like this. So initially I had the first column itself pre-ready, so I have it pre-ready, cool, no worries. Then I just updated this value of current 0, which is nothing but, as I showed you, existing current 0 plus grid of I, so as to get this value. Now I can just go on iterating. So to grab this value, it's nothing but the current 0 plus the left one, which is current of 1, or the I minus 1 to be more precise, because I'm just moving like this, and current of I can get. So current of 0 is here, current of 1 was here, which means I and I minus 1, and also adding the grid value. With this, I can just move in like this, column, 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 column. For the first row specifically, as it has no top, so I'm just specifically marking how it can get the value. It can only get the value from left. Else for every other case, I can get a value from both left and right. As simple as that. I hope that you guys understood it. Every method 1, 2, 3, 4 with recursive. We also thought of recursive, how the recursive will work. I hope that you guys liked it. It was a complete intuition of the problem from scratch. And yeah, I hope that you guys liked it. If yes, then do the like button, and see you in the next video. Goodbye. Take care.